Welcome back to the Explainer. So today we're diving into what is arguably one of the most powerful and honestly absolutely essential tools in advanced math. If you're grinding through calculus right now, you already know finding the area under a curve is super useful, right? But man, the math to get there can turn into a tangled mess real quick. Well, we're going to fix that today. We are focusing squarely on the specific steps for solving integration problems by mastering a technique that literally changes the game. Okay, let's talk about that frustrating mathematical roadblock. The fundamental theorem of calculus is fantastic, obviously. It gives us a neat way to evaluate integrals without having to rely on those tedious Riemann sums. But there's a massive catch. You actually have to be able to find an antiderivative first. And look, as anyone who's stared blankly at a complex integration problem knows, standard rules just don't cut it when you're dealing with a messy, layered compound expression. You just kind of hit a wall. So, how do we bypass this roadblock? We use a little trick called integration by substitution. I want you to think of this as a clever mathematical disguise. When we're staring down an intimidating, complex problem, specifically one born from a chain rule derivative, we basically slap a temporary mask on it. We literally change the variables to transform a terrifying equation into something super familiar and easy to solve, and then we just pull the disguise off at the very end.
Here's our quick roadmap for this explainer. First up, the chain rule reversal. Then, we'll hit the core 5 steps to substitution. After that, indefinite integrals in action. Next, altering the constants. And finally, tackling definite integrals. Let's get right into it.
Section 1, the chain rule reversal.
Now, what's really fascinating here is the specific pattern we're hunting for. Basically, you're scanning your equation for an inner function, let's call it g of x, tucked inside another function. But here is the absolute secret sauce. That inner function must be multiplied by its own derivative, g prime of x. If you can spot a function and its derivative just hanging out right next to each other in the same integral, boom, you've found the perfect candidate for substitution.
And I absolutely love how the source material puts this. It points out that this is primarily a visual task. The math is literally showing you what to do if you know how to look for it. You're training your eyes to spot that inside function and its derivative pairing. It's almost like a game of visual matching before you even pick up your pencil to calculate anything. But, once you visually spot that pattern, you need a rock-solid strategy to actually solve it.
Which brings us to Section 2, 5 steps to substitution.
All right, if there is one thing to take away today, it's this. To master the steps for solving integration problems, you've got to memorize this exact 5-step framework. Step 1, pick your inner function, your g of x, and call it u. Step 2, find the derivative of that u, which we call du, and substitute both u and du right into your integral, completely wiping out the x terms. Step 3, pause and check. Can you actually evaluate this new integral? If you can't, you probably picked the wrong u, and you need to back up and try again. Step 4, do the actual integration using your basic rules. And Step 5, take the mask off. Replace that u with your original x expression to get your final answer. Easy, right?
Let's see this in Section 3, indefinite integrals in action.
Taking a look at example 5.30, you can see these 5 steps working flawlessly. We're integrating 6x times the quantity 3x squared plus 4 raised to the 4th power. Step 1, we isolate that inner term, the 3x squared plus 4, and set it as our u. Now, the derivative of that is 6x dx, which, wouldn't you know it, perfectly matches the rest of our equation. So step 2, substitute. The whole messy equation just collapses into the integral of u to the 4th power du. Steps 3 and 4, we just knock that out using the power rule, getting u to the 5th over 5. And finally, step 5, we swap the original x expression back in. Disguise comes off, problem solved. But hey, what happens when the disguise doesn't fit perfectly right out of the box?
That takes us to Section 4, altering the constants.
So sometimes, when we take the derivative of our u to find du, it spits out an extra constant that just isn't sitting in our original equation. Say our derivative is 2z, but our original integral only has a z in it. Well, we can't substitute du directly because it's literally twice as large as what we actually have. So to fix this, we just use some basic algebra. We divide both sides by 2, sliding that constant over, which creates an expression that says 1/2 du equals z dz, and now it's a perfect match. Let's visualize that with example 5.31. Notice how we have a z in the original equation, but our do calculation gave us 2z dz. By just multiplying both sides of our do equation by 1/2, we fashion the perfect puzzle piece to substitute in. And honestly, here is the best part. We can yank that 1/2 fraction entirely outside the integration symbol. This clears the deck so we can easily evaluate the nice, clean u integral without letting messy, annoying constants disrupt our nice 5-step process. Finally, Section 5, Tackling Definite Integrals. Now lean in for this one because this is where a lot of people trip up. The absolutely unbreakable rule for definite integrals is consistency. Your limits of integration on the graph are tied directly to the specific variable you are working with. So if you change the variables in your integrand from x to u, putting that disguise on, you absolutely cannot use the old x boundaries anymore. No way. You have to update the limits of integration to match the new u variable. And you do this by simply taking your old boundary numbers and plugging them straight into your newly created u equation. Let's see how this sharpens our final skill. In example 5.34, our original limits are bounded by x equals 0 and x equals 1. But remember, we substituted u to equal 1 plus 2x cubed. So we've got to update those limits. We plug the 0 into our u equation and boom, we get a new lower limit of 1. We plug the 1 in and we get a new upper limit of 3. Notice how those numerical boundaries physically transform right there in the equation. We can now evaluate the whole thing using 1 and 3. And here is a fantastic shortcut for you. Because we updated the boundaries to u, we just solve the math right there to get our final numerical answer. We don't even have to change back to x at the end. To wrap up this explainer, I really want to leave you with a fascinating puzzle pulled directly from the text's exercises. Check out this potential substitution for an integral bounded from 0 to 2. Is this substitution actually allowed? Think deeply about what happens to the math when you look at the denominator of the original equation, which is 1 minus x squared. If our bounds go from 0 to 2, what exactly happens right in the middle at x equals 1? Well, the denominator becomes 0, entirely breaking the foundational rule that our function must be continuous over the whole interval. It's such a great reminder that while our 5-step framework for solving integration problems is an absolute powerhouse, you always have to keep your eyes open and really look at the math in front of you. Thanks for joining me on this explainer, and I hope you feel totally equipped to start tackling substitution on your own.